Alright, I will continue solving the problems of version E for the first midterm. And so we finished with the 10th problem, and I will just go on. So the 11th problem is rather straightforward, but you need to know how to actually do this. Please check it out. It's a little boring to solve this one. But again, so please check it out. A problem like this might be on your exam. This is just a transformation of moles and eventually to the number, and the number eventually to the coulombs. Okay, but you need to know that. So we've done that multiple times. You did it in your homework as well. Please refresh this knowledge. Okay, so now let's consider the next one. 12. Consider a positively charged solid metal sphere. So we have a solid metal sphere, and we are said what is correct about this solid metal sphere. The first one, the net electric field is zero at the center of the sphere. That's definitely true. The net electric field is zero at the center of the solid sphere in static equilibrium, no matter where actually, not only in the center, anywhere in this sphere, in this solid sphere, the net electric field is zero. So let's move on to the next one. So in the next one, we have the arrangement shown over here. We need to find the direction of the net electric force on Q3. Okay, very good. So we are going to define the direction of the force which is exerted by the charge 1 on the charge 3. Well, they are of the same charge, so they repel each other. This will be F1. So now but F2, the charge Q2 has a negative charge, so the opposite, so charge Q3 is attracted to the charge F2. Okay, so now I can find a vectorial sum of these, so it will be something like that. So this will be F net. Okay, these are all vectors here. F net, so, and its direction will be 4. Direction 4 corresponds to the answer A. Okay, next one, number 14, and number 14. Now we have spheres over here. What we need to find the electric field at location A, its magnitude. Okay, very good. So let me just denote this distance from the center of these spheres to A by R. Okay, so I will just, so this R equals to A times 10 to the negative 2 meters, right? So, but I will just denote it by R. So then I will compute the electric field, okay, at the point A, which is generated by the charge Q1. Okay, it is K times Q1 divided by the distance to this point, R squared. Okay, so that's the magnitude of this electric field. And let's consider actually not only the magnitude by the vector at point x, at this point. So let's say this is x direction. So the x component of this field will be just that. Okay, there is no other contributions over here. It will be just that. Okay, so what about the electric field 2, which is generated by the charge in this shell? Okay, it's the same equation. It's just instead we use Q2. It's also divided by R squared because we are computing the distance between the center of that shell of charge to that point A. All right, so to find the net electric field, we just add the vectors by adding the vectors. So by the way, so y component E1, y, E2, y. Well, in this case, they are just zeros. Yeah. Okay, so the net component, the net electric field, so it will be only in the x direction, will be just the sum of k q1 divided by r squared plus k q2 divided by r squared. Well, we can just compute the sum, we will obtain k q1 plus q2 divided by r squared. We need to substitute the numbers. We should remember that q2 is actually negative. Okay, so we will substitute the numbers, so q2 is negative, and get the final result. Okay, don't forget that r squared is also r is given, so it's over here. Let's move on. Okay, this is a conceptual one. It's also pretty straightforward. I will let you do that. Let's look over here. Okay, so we are given the Van der Graaf generator. Okay, so essentially we have a thin shell, a thin metal shell. It has some radius. Okay, the radius is not given. What is given is diameter, and the radius is diameter divided by 2, right? So the radius is 0.35 meters in this case. Okay, okay, so then the charge, or the net charge on this sphere is 1.7 microcoulomb. Okay, very good. So what we need to find the electric potential on the surface of the sphere. Well, for the electric potential of the sphere, we have the equation, which is K times the charge divided by the radius. Okay, the radius to the point where we compute the potential, but in this case this radius coincides with the radius of the sphere, right? Because we want to find the potential on the surface of the sphere. Okay, well, that's essentially the answer. We just substitute the equations, substitute the numbers, and we'll find the solution. I think it's D. All right, so let's consider 17. In 17, the 2-point charges. Okay, so we have 2-point charges. Their distance r away from each other. Very good. So the charge is not given, but let me say that this is q1 and this is q2. Okay, fine. So actually the force, so let's say the force which would act on q2, F1. Okay, so the force F1 is given by what? So it is K, the Coulomb constant, times Q1, and I will be talking about the magnitudes, of course, Q1 times Q2 divided by the distance between them, which is capital R squared. Okay, then we said that the same charges, so the same arrangement, so this Q1 and this Q2, but we have the same arrangement, but now their distance 3 times r apart. Okay, and we need to find the force for this situation. Let me call this let me call this f hat. Okay, not a good notation, I don't know, f tilde. Okay, this is when I move them the distance, which is 3 times r apart. Okay, so what equation do I use? Well, I use the same equation, q1 q2, right, the same charges, divided by, well, the distance between them, and the distance between them is 3r squared. Well, or I can simplify it a little bit, so just open up the brackets. I will get k times q1 divided by q2 divided by 9r squared. But here you can already recognize that this was our original force, so it will be 1/9 of that original force F1 when they were distance r apart. Okay, but this F1 is given, right? So this is that. I need to just divide it by 9 and I will get the final result. So as a matter of fact, so if you know that interesting fact, that 2 divided by 9 is actually 0.2222. Okay, so as a matter of fact, any number, like say, I don't know, 7 divided by 9 is also 0.777777. Okay, so, and therefore it is very easy to compute the answer to this problem. Let me remove all that. it's easy to compute the answer to this problem because F is 2 times 10 to the negative 5. Okay, so let me just actually compute this for you. So I have 1/9 times 2 times 10 to the negative 5 Newton. Okay, and that combination, I know that is 0.2222. Okay, so in other words, it is 2.22 times, etc., times 10 to the negative 6 Newton, right? So that's this answer. Okay, let's move on. So let's consider now 19. I will remove that because I have no space. Let's consider 19. So in 19, okay, so we need to find the electric field at this point. Okay, electric field is not known. Well, the first thing we're going to do, we're going to define this axis as to be as an x-axis. Okay. Next thing is we're going to find the components, the electric field, which is generated by each charge in separation. We will start with the charge number 1. So we consider or we think that at this point there is a positive test charge. Since it's a positive test charge, then electric field E1 will be directed in this way, right? Because they repel, and this will define the direction of the electric field. Now about the charge Q2, it's also positive. Okay, so they also repel, so this will be E2. E2. And of course these are vectors, but these vectors have only x components, so it's pretty straightforward than the algebra we are going to use. So let's start with E1 and its x component. Its x component will be of course given by the magnitude, and we know how to find the magnitude of the electric field. Distance r, let me say that this is r, and this, as you can see from this picture, will be 2r. Okay, so it's 4, it's 8, so it's r and 2r. So r in my case is 4 times 10 to the negative 6 meters. Okay. E1x. So E1x, so the x component of the electric field, will be given by the Coulomb constant times Q1 discharge divided by the distance to this point, and it is r squared. Okay, so what about E2x? Oh, and by the way, it is with positive sign, right? With positive sign. As you can see, the direction of this electric field coincides with the direction of my x-axis for E2x. Well, here you see that here the direction of the electric field is opposite to the direction of the x-axis, and therefore I should not forget to put minus sign over here. Okay, then I will just continue writing. Now I have a Coulomb constant. Now I have this charge Q2. Now it is divided by the distance to that point from the charge Q2, and it is 2r. Okay, again, you can substitute the numbers at all points. I just prefer right now to use not to use the numbers. Okay, very good. So now I can find E net, and again, it's x component, right? So it will be E1x plus E2x. Okay, I just substitute. I will get k. Okay, k times q1 over r squared minus. I'm not forgetting about this minus, right? Minus q2 divided by 2r squared. Okay, anyway, so at this point you just can substitute the numbers over here, you can substitute the numbers over here, and finally you'll be able to obtain the final result over here. Don't forget that there is a negative sign involved because E2x is negative, okay? But you will get the final result. I'm not going to compute that, it's pretty straightforward, I will let you do that. Now, okay, let's consider the next problem. A negative charge is placed in the electric field as shown below. Okay, given the equipotential line shown in the figure, which direction will the negative charge accelerate as a result of the electric force? Very good. So now we have to remember, so this is equipotential lines. How do we decipher the direction of the electric field from equipotential lines? And we have to remember that the electric field is directed from high to low potential. This is encoded by this equation that delta V is minus EX times delta X. Okay, this is encoded in this equation, but let me note, I'll try to decipher it from here. You just can remember it's conceptually, so this minus is essentially tells you that I will just you probably should just remember conceptually that the electric field is directed from high to low potential, and so on here. Very good. So this electric field, what next? So next, of course, so given this electric field, so this electric field is here as well, right? So given this electric field, we need to find the force on this charge. Well, we know how to find the force. So force, it's vector, right? It's given by the charge Q times the direction of the electric field. But the charge, as is shown over here, is negative. Or in other words, I can rewrite this as minus absolute value of this charge. Okay, so I factored in my knowledge that this charge is negative times the electric field. So we see that the direction of the force is opposite to the direction of the electric field due to this minus sign. Okay, so the direction of the force will be opposite in direction to the direction of the electric field. Let me show it over here. So this will be the direction of the force vector. Okay, so it means it's negative x direction. That's it for this exam, and next time we are going to refresh the midterm number 2.